Hello everyone, and welcome back. In the past couple of videos, we've been investigating the theory and some applications of eigenvalues and eigenvectors, and from those things we were able to construct what is known as an eigenvalue decomposition for a square matrix A, provided that that matrix, of course, had an eigenvalue decomposition, which of course required it to, for example, have eigenvectors that span all of the n-dimensional vector space for which its columns should span. Now, with that being said, not all square matrices have eigenvalue decompositions, and of course, up to this point, we have not really defined eigenvalues for rectangular matrices, so of course rectangular matrices also do not have eigenvalue decompositions. So it would be nice if possibly we have a decomposition for a matrix, in particular any matrix, that always exists regardless of its structure. And that is pretty much what the purpose of singular value decompositions aims to serve. Now, before we get into actually developing the singular value decomposition of a matrix, let's just review a couple important properties of eigenvalues for matrices. So let's assume, just for the sake of conversation, that A is a symmetric matrix. In particular, the transpose of this matrix is equal to the original. And let's also assume that lambda is an eigenvalue of A. So what are some of the important properties associated to symmetric matrices and eigenvalues that we should be able to prove up to this point? So the first one that you definitely should know is that the eigenvalues of symmetric matrices are always going to be real numbers. Also, another important fact is that if lambda is an eigenvalue of A, then lambda is also going to be an eigenvalue for A transpose. So if lambda is an eigenvalue for A and the transpose of A, one should be able to show that the eigenvalues of the matrices A transpose A and AA transpose are going to have the eigenvalues of the form lambda squared, where lambda is an eigenvalue of A, right? So that's also a very important thing to note. So this means that the eigenvalues of A transpose A and AA transpose, which we can give them a name, for example, eta, then we see that the eigenvalues of A transpose A and AA transpose are always going to be greater than or equal to 0. So what we usually call these matrices when the eigenvalues are greater than or equal to 0 is we call them semi-positive definite matrices. Semi-positive definite matrices. And if you have eigenvalues that are always strictly positive, then we call those matrices positive definite matrices. And you can also define, for example, negative definite and semi-negative definite matrices using similar principles. But we're only going to be focused on semi-positive definite matrices. So since they are real numbers and they're always positive, that means when we take the square root of these values, we're also going to get a positive number as well. So we're always going to get something that is greater than or equal to 0. So that's something very important to keep in mind. Also, one very important thing about symmetric matrices is that they always have eigenvalue decompositions. So let's assume, for example, that the characteristic polynomial of our symmetric matrix A has the factorization lambda minus lambda 1 to the power of mu 1 times lambda minus lambda 2 to the power of mu 2 all the way down to lambda minus lambda, say, k to the power of mu k, where 1 is less than or equal to k is less than or equal to little m, and the sum of these mu's, mu1 plus mu2 all the way out to mu k must be equal to m. So if all of the eigenvalues are distinct, then all of these mu's are going to be equal to 1, but of course you can have some eigenvalues that repeat. So that's actually, this factorization actually always exists for even matrices that are not diagonalizable, but in particular for symmetric matrices, the dimension of the associated eigenspace for, say, lambda is equal to lambda subscript j is actually equal to mu subscript j. So these numbers, mu1, mu2, down to mu k, are sometimes referred to as the algebraic multiplicities, and the dimension of the associated eigenspaces for those eigenvalues are called the geometric multiplicities. So what we have here for diagonalizable matrices is that the sum of each of these things are always going to be equal to m, and the geometric multiplicity and the algebraic multiplicity are always going to be equal to each other. And that, of course, gives us the result that all symmetric matrices have eigenvalue decompositions, which is very, very nice. But of course, eigenvalue decompositions or symmetric matrices only apply to square matrices. So how do we extend this to matrices that are not symmetric or moreover are not square? So with these basic things about symmetric matrices, let's actually look at an example and look at its eigenvalue decomposition just to get a little bit of insight. So let's consider the 3 by 3 matrix, 5, 8, minus 4, 8, 5, minus 4, and minus 4, and minus 1. So I invite you to try and figure out, for example, the eigenvalues and eigenvectors of this matrix on your own before I give the answer, just in case you want to practice. But if you're already confident about how to find these things, then that's perfectly okay too. So the characteristic polynomial of this matrix A can be defined, for example, as the determinant of lambda minus AI or AI minus lambda. Actually, A minus lambda I. A minus lambda I. A minus lambda I, or some people like the lambda I minus A approach, right? Which is actually the approach I'm going to do here. And the reason why some people prefer the definition of characteristic polynomials as lambda I minus A is because that's always going to be a monic polynomial. In particular, the leading coefficient is always going to be positive 1, where in this case it's going to be positive 1 for even degrees and negative 1 for odd degrees. So it creates a bit of confusion for some people. So usually this one is a little bit more preferred, but both give the same eigenvalues. And if you know the Cayley-Hamilton theorem, it provides the same results there because you can multiply both sides by negative 1 for the 0 and you still get the same exact polynomial. So that's not a big deal. So if we approach it via that approach, then one can find that the characteristic polynomial is going to be equal to lambda cubed minus 9 lambda squared minus 81 lambda minus 135, which one can factor into lambda plus 3 the quantity squared times lambda minus 15. So that's the factorized version of your polynomial. And if this was an arbitrary matrix, that is the 3 by 3. Obviously, if you look at, for example, the eigenspace for lambda is equal to 15, we should already know that the dimension of that is going to be equal to 1 guaranteed. But this matrix here, so the dimension of the eigenspace associated to negative 3, we know that this is going to be anywhere between 1 or 2. And if it is equal to 1, then we know that the matrix is not going to be diagonalizable. But if it is equal to 2, then we have that 2 plus 1 is equal to 3, which is going to be the full possible rank of that particular matrix. And hence, we have 3 independent eigenvectors, and then we are done, right? But one thing that is very useful about symmetric matrices is the dimension of the eigenspace, the geometric multiplicity, is always going to be equal to the algebraic multiplicity, thus forcing us to always have an eigenvalue decomposition for symmetric matrices, right? So what do we have here? So we have that eigenvalue 1 and eigenvalue 2 are both equal to minus 3, and eigenvalue 3 is equal to positive 15. So we have 3 eigenvalues, 2 distinct eigenvalues. So for example, what is the basis for these 2 eigenspaces, right? So one can find that the basis for the eigenspace associated to lambda is equal to negative 3 can be equal to the following 2 vectors, 1, minus 1, 0, and 1, 0, and 2. Right, so those are our 2 vectors, u1 and u2, let's say. And a basis for the eigenspace associated to eigenvalue equal to 15 can be the vector 2, 2, and minus 1. Right, so one can be able to verify that, of course, u1, u2, and let's call this, for example, u3, are all independent eigenvectors, and hence the eigenvalue decomposition will be defined. For example, the eigenvalue decomposition of that matrix is just going to be equal to u1, u2, and u3, all columns, times our minus 3, 15 diagonal matrix, and then u1, u2, and u3, the inverse of that. And we know the inverse of that does exist because these columns are independent from one another, so that's very nice. Now, although the eigenvalue decomposition of this does exist, and that's not just true for symmetric matrices, it's true for many. But one important thing that you definitely should know is something special about these vectors u1, u2, and u3. In particular, if you take the dot product between ui and uj, with I and j not equal to each other, you're always going to get equal to 0, i.e. these vectors are orthogonal to each other, right? And that's, of course, for I is not equal to j. So we say that these vectors are mutually orthogonal to each other. right? So if that is the case, keep in mind you don't have to choose these eigenvectors. You could choose any scalar multiple of them. What you can do is you can choose these vectors to be unit vectors, right? So you can, for example, divide this vector by the square root of 2. You can divide this vector by the square root of 5. You can divide this vector by the square root of 4 plus 4 plus 1, 9. So you can divide that by 3. And then you're going to have unit vectors. And then what you're going to have here is you're going to have two matrices that are orthonormal matrices, right? So these can be chosen to be orthonormal. So chosen to be, not necessary, but chosen to be orthonormal. And then when we want to find the inverse of that matrix, all we need to do is just take the transpose, and that will actually give us that inverse matrix, right? So what we have here is an orthogonal diagonalization. So we have an orthogonal diagonalization. Orthogonal diagonalization of A, where these matrices U and the matrix before we invert it are orthonormal matrices. Now let's just give a couple terminologies of things just to be clear. So diagonalization is usually referred to eigenvalue decompositions. And we've already proven that the only way you can actually diagonalize a matrix is via what is called its eigenvalue decomposition. And if we want to orthogonalize a matrix, which is in verb form orthogonalization, then what we need is eigenvectors that are orthogonal. So eigenvectors that are orthogonal to each other. That's what we require, and one can show that the only way that we can construct an eigenvalue decomposition for which those matrices of eigenvectors are orthogonal to each other is true if and only if the matrix for which we're trying to diagonalize is indeed a symmetric matrix. So therefore, only symmetric matrices have orthogonal eigenvalue decompositions. Right? So that is one special thing about symmetric matrices. Right? Now let's sort of zoom back into the main point that we're sort of targeting here. So keep in mind, not all matrices, in particular not all square matrices, have an eigenvalue. Some people just say eigen decomposition. And that's okay because we have a decomposition for every matrix in a moment. Right? So let's assume for the general case, because we're trying to find a decomposition for the rectangle matrix, so let's assume A is an m by n matrix. So remember that if we take the transpose of A and multiply it by A, this is always going to be a square matrix. In particular, it's going to be an m by n matrix, so it is a square matrix. And if we multiply A by its transpose on the right-hand side, that is going to be an m by m square matrix. So both of these are square, and in particular, both are square symmetric matrices. And that is something that you definitely should be able to prove at this time. In particular, the eigenvalues of these matrices are actually always going to be positive. So these matrices, and you can take this as a theorem if you want, these are always positive semi-definite. These are always positive semi-definite matrices. Right? And the proof of that is a little bit more trickier than it might meet the eye, because keep in mind this does not have eigenvalues. So you can't just say, oh, well, the square of those values is always greater than or equal to 0. Well, that's only if you can define an eigenvalue for a rectangular matrix, right? So for the squares case, it's trivial. But in particular, even if A is not square, the eigenvalues of these are always greater than or equal to 0. So what would we like to have for the decomposition of a rectangular matrix A m by m? So we would like it to at least have the same exact structure. For example, we want m by n to be decomposed into, for example, a matrix U, which would be like, we would like it to be a square matrix so we can invert it. And then we have a rectangular matrix D, which is going to be sort of like our diagonal matrix in our eigendecomposition. And then we would like V to be, for example, an m by n matrix. And of course, we're going to be inverting that. But if we take these matrices, U and V, to be, for example, unitary matrices in the complex world or orthonormal matrices in the real world, then that would just need to be changed to transpose. And this, once you can find them, is what is referred to as the singular value decomposition of the matrix A, which some people just abbreviate as the SVD of the matrix. So now we know the structure of the decomposition that we aim for. Now we need to just be able to figure out how to find it and how to show that it always exists for any matrix A that is an m by n matrix. So let's first off review just a couple basics about what the matrix A, m by n, actually represents from the transformational perspective. So recall that a matrix that is A, an m by n matrix, and let's assume that it's a real valued matrix, right? So let's assume all of its values are in the set of reals. So then we know that this matrix is an homomorphism from the vector space Rm into the vector space Rm. Right? So let's, for example, take a vector x belonging to Rn, and let's choose another vector y belonging to Rm. And if A maps Rn to Rm, in particular it maps x to y, then we have that Ax must be equal to y, right? And again, let's assume that x belongs to Rn and y belongs to Rm. So if we draw a geometric representation of this, right? So let's assume that this set corresponds to Rm, and let's assume that this is another circle representing the set Rm, which of course is very simplified drawings of these really large vector spaces, right? So let's assume the 0 vector is there, and let's assume our little x vector is there, and let's assume that the 0 vector of Rm is there, and let's assume that this vector y is the vector that we want, right? So let's actually draw some horizontal references for this vector here, and let's draw that vector there. So what this matrix A does is it sends this vector x to this vector y. So that's what A does. So if we try to represent A as this singular value decomposition, in particular A is equal to U d V transpose, actually I just want to write it as inverse even though we know it's a transpose if A and U and V are unitary matrices. What does that decomposition actually represent? So if we have, for example, Ax is equal to y, and we replace A with u dv inverse, then we have that u dv inverse times x must be equal to y. So we're applying this transformation onto x. And keep in mind, the first transformation that needs to be applied is going to be v inverse, then followed by d, and then followed by u, and that's going to give us the vector y. So if we represent this in the same exact world, so let's, for example, take a look at the world Rn. Keep in mind, V is an m by n matrix, so V inverse also is going to be an m by n matrix. So if our vector x is located here, let's assume this is our point vector of reference. So keep in mind, if U and V are orthonormal matrices, in some sense they are just rotation matrices. So what V inverse times x is going to do is it's just going to rotate this vector x down to here. So this vector here is the vector V inverse x. So the next thing that we need to do is map this rotated vector over into this new space here. Right? So let's assume that this is our 0 vector here. Let's assume that this is our vector point of reference. So now we need to apply the next transformation, which is going to be d. So d is going to, 1, translate it from Rn into Rm, and also scale it. So keep in mind the vector y that we're aiming for is going to be this vector here in gray. So what the matrix D is going to do to the vector V inverse x is it's going to map this orange vector into this vector here. So this vector has the same length as the vector y in Rm. So this is going to be dv inverse x. All right. So D scales and transforms dimensions. All right? Because keep in mind, U and V are square matrices, so they don't transform the dimensions, they just transform the space, right? So the last thing that we need to do in terms of getting to Y is we need to rotate that. right? So we need to rotate that by some angle, say theta, so we need to apply some orthonormal matrix, which we represent by u. So that means this vector is going to be represented by u times dv inverse x, which is just the same thing as ax, which is of course going to give us the vector y, right? So that's pretty much what the singular value decomposition, or the SVD of a matrix, actually represents geometrically. That is, every transformation from one vector space to another can be in a sense represented as two rotations and a scaling transformation. Now, one thing is still left. How to find u, d, and v. This is the very fun part, right? Because now we know what we're looking for, we know what it's going to do, now we need to be able to find it. Hopefully always. Okay, so let's see if we can build a nice algebraic argument. So let's suppose that A is equal to u dv inverse with u and v unitary matrices. So I'm allowing A to be a complex valued matrix here. So if that's the case, then A transpose is going to be equal to the transpose of u dv inverse, right? Keep in mind, V is a unitary matrix, so that means this is also going to be equal to u dv transpose. And keep in mind, when we apply a transpose to a product of matrices, it reverses the order. So we're going to have the transpose of V transpose, the transpose of D, and the transpose of U. Right? So the transpose of a transpose is just going to be the original matrix, so we're going to have V times dt times ut. All right? So if that's going to be equal to AT, then what happens when we multiply everything on the right-hand side by A? So that's going to be equal to V dt ut times A, which is A d or ud V inverse. So u d V inverse. Right, that looks like a B, so let's make sure that looks like a D. Right, so keep in mind matrix multiplication is associative, so I can write this as V dt ut u in parentheses D times Vt. And keep in mind A or U is a unitary matrix, so the transpose is its inverse, so that just cancels out to the identity. So we have that A transpose A is going to be equal to V times D transpose D times V transpose. Right, which is technically the inverse of V, but I actually want to write it as inverse so this actually becomes clear. So keep in mind, this is a matrix and it has this representation. One should be able to show that D, if D is a diagonal or a pseudo-diagonal matrix, then DT also will be a pseudo or full diagonal matrix. In particular, regardless of D is a pseudo-diagonal, whatever that even means, one should be able to show that DTD and also DDT are actually full square diagonal matrices. These are always going to be square diagonal matrices. And if you don't know what I mean by pseudo-diagonal matrix, I'm talking about matrices that are like 5, 0, 0, 3, 0, 0, where that's practically the best you can do with a 2x3 matrix in order to make it what we call pseudo-diagonal. Right, so we have a diagonal matrix in the middle, so what we've done is we've created a diagonalization of the matrix ATA. And keep in mind that ATA is always a square matrix. Therefore, keep in mind, this is going to be a eigenvalue decomposition because that's the only way you can diagonalize a matrix. So this is the eigenvalue decomposition. So what is in the vectors V and V inverse? So that would be the eigenvectors of ATA, and the elements of DTD will contain the eigenvalues of ATA. So we know what the matrix D is now, and we know what the matrix V is now. But we're still missing part of the picture because we still do not know what U is, right? So if we apply the similar logic, what would AAT be equal to? So that's just going to be equal to U dV transpose times V times D transpose times U transpose. And as usual, VT times V is going to cancel. And we're just going to be left with U D DT, which is the diagonal matrix, times UT. Keep in mind, this is again a diagonalization of the matrix AAT, but what's in the matrix U now? So that's going to contain the eigenvectors of AAT And the matrix DDT is going to contain the eigenvalues of AAT. Right? Now, it's very important to note that if A is a rectangular matrix, ATA and AAT will not be the same exact size. But there is something very, very important about the eigenvalues. In particular, the eigenvalues of these two matrices are the same, aside from the other eigenvalues that are needed to fill the gap in terms of their dimension. In particular, if one is a 5 by 5 and one is a 9 by 9, the 9 by 9 matrix is going to have at least 4 zero eigenvalues to fill in that space. And one could, of course, prove that algebraically if one is interested. So let's just look at a brief, quick example. So let's assume A is a 3 by 5. Then D times dt is going to be a 3 by 3. So what is going to be, for example, the characteristic polynomial of d dt in terms of lambda? Let's pretend, for example, that this is going to be equal to lambda minus 3 squared times lambda plus 5. Let's pretend, right? So what would the characteristic polynomial of d dt be? So keep in mind d dt, or dtd, will be equal to a 5 by 5 matrix. You should be able to prove that. And the characteristic polynomial will be a degree 5, so dtd of lambda would be equal to what? Well, it's going to have the same non-zero eigenvalues, so lambda minus 3 to the power of 2 times lambda plus 5. And notice that's only 3, so we need 2 more, so that's going to be lambda squared. And one, of course, should be able to prove that in a more rigorous way, right? But the non-zero eigenvalues are going to be the same for both ddt and dtd. So even though A does not have any eigenvalues, in some sense, the eigenvalues should be the square roots of these positive things, right? And technically you shouldn't be able to get that negative thing for symmetric matrices, but this is just a little example just to illustrate it. But now we at least know what these matrices U, D, and V should be. So we have that U should contain the eigenvectors of AAT. We have that V should contain the eigenvectors of ATA, and keep in mind that these vectors need to be unit vectors. And since AAT and ATA are symmetric matrices, those eigenvectors are going to be orthogonal. So once we make them unit vectors, the matrices U and V will be unitary, and that is actually always going to be the case. And D is going to be the square root of the eigenvalues of ATA or AAT, it doesn't really matter which. And the square root of the eigenvalues of these things are referred to as the singular values of the matrix A. So, how many singular values does an m by n matrix have? So if we have an m by n matrix, then A will have the minimum of m and n singular values, right? Because the difference between m and n is just going to be a bunch of zeros, so that's not really useful. And then once we have A is equal to U dV transpose, this is called the singular value decomposition of the matrix A. And up to that point, we have shown that every matrix has a singular value decomposition, and this is how you find those matrices U, D, and V. Now let's look at a couple examples on how to find them, and look at a couple consequences that we get from that. Let's consider this very nice looking 2x2 matrix. So we see it's an upper triangular matrix, so the eigenvalues are actually quite easy to see. So we have that the eigenvalues are repeated, in particular lambda 1 and lambda 2 are both equal to 1. So one should be able to show that the dimension of the eigenspace associated to the eigenvalue of 1 is actually equal to 1 and not 2. Therefore, the algebraic and geometric multiplicities are not equal to each other, therefore this matrix is not diagonalizable, which is kind of sad because the matrix looks a bit nice. But keep in mind, although it doesn't have an eigenvalue decomposition, it does have an SVD, because all matrices has SVDs. So what do we need to do in order to find the singular value decomposition of this matrix? So the first thing that we need to find is, for example, A transpose A, and then we also need to find AA transpose, because the eigenvectors of ATA is going to help us construct the matrix V, and the eigenvectors of AAT are going to help us construct the matrix U. So once you find that ATA is equal to 1, 1, 1, 2, and AAT is going to be equal to 2, 1, 1, 1, then you can find that the eigenvalues of 1, 1, 1, 2 are going to be lambda is equal to 3 plus or minus the square root of 5. So 3 plus square root of 5 and 3 minus square root of 5. So let's actually write them out. So 3 plus the square root of 5 and 3 minus the square root of 5. Now keep in mind these are square matrices, so they have the same exact number of eigenvalues, and you should know what these next eigenvalues are. You don't actually have to find them. They're actually going to be the same thing, so 3 plus the square root of 5, and again 3 minus the square root of 5. Now, these eigenvalues are not the prettiest of eigenvalues, but you can still find eigenvectors for them. That is no big deal. For example, for the 3 plus the square root of 5, you can find that the first eigenvector is going to be negative 1 plus the square root of 5 over 2 and 1. And the second eigenvector, v2, is going to be equal to negative 1 minus the square root of 5 over 2 and 1. And then for this other matrix, we're going to have slightly different eigenvectors. So we're going to have u1 is equal to 1 plus the square root of 5 over 2 and 1. And then u2 is going to be equal to 1 minus the square root of 5 over 2 and 1. Once you have your eigenvectors, you then need to make sure that these are the correct eigenvectors that you want to use. So you need to take the norm of each of these vectors, which is definitely not the nicest of norms, and we need to make all of them, so make them unit vectors. So that's going to give us, for example, vectors u1 prime, u2 prime, v1 prime, and v2 prime, right? So these are going to be the unit vector versions of these two. There's one other small little caveat that you need to keep in mind, but we'll mention that in just a moment. So once you have your eigenvectors, that's going to help us build our matrices U and V, and we have the eigenvalues of A transpose A and A transpose. We then need to take the square root of those positive or non-negative eigenvalues, and that's going to construct our singular values. So the first singular value is going to be the square root of 3 plus the square root of 5, and the second singular value is going to be the square root of 3 minus the square root of 5. So once we have our singular values and our vectors, then we have that our singular value decomposition of our 2 by 2 matrix is going to be equal to our u1 prime and u2 prime vectors that we found once we made them unit vectors. And then we have our D matrix, sigma 1 and sigma 2, which is also going to be a 2 by 2, and then we're going to have v1 and v2 prime on the rows of that last matrix. That's after you take the transpose of it, right? So this is what we call the singular value decomposition. Now, one big requirement, keep in mind that these both are unitary matrices. They must have the same determinant. So they must have the same determinant. Because keep in mind, unitary matrices can either have 1 or negative 1 as their determinant. If you do not have the same exact determinant, the singular value decomposition will be a bit off. So you do need to make sure that you have the right orientation for your eigenvectors, because you know you have that bit of freedom when you scale them. But the requirement to make sure that the direction of this rotation and that rotation match is generated by the requirement that they have the same exact determinant. Either both of them are 1 or both of them are negative 1. It doesn't matter, but those determinants have to match, else the determinant of A is not going to match the determinant of the right-hand side. So make sure that you do have those determinants matching in the end. The next example that we're going to look at for an SVD is more interesting than the last, because at least this definitely doesn't have an eigenvalue decomposition because it's not even a square matrix, right? In particular, we have a 3 by 2 matrix on our hands. So what is the very first thing that we need to find? Well, we need to find, for example, A transpose A. That's actually going to be our pretty 2 by 2 matrix, and one can find that that's actually going to be equal to the diagonal matrix 2, 0, 0, and 3. So the eigenvalues of this are obviously going to be 2 and 3, and you should be able to find associated eigenvectors, and these are actually pretty easy because it's a diagonal matrix. So V1 you can probably guess is going to be 1, 0, and the second eigenvector is going to be 0, 1. Both are unit vectors, so we don't need to normalize them, which is actually pretty great. And keep in mind, these are going to help us construct the matrix V. Once we have ATA, then we can look at AAT. So AAT is going to be a 3 by 3 matrix. This is going to be equal to 2, 1, 0, 1, 1, 1, and 0, 1, 2. So we're going to have 3 eigenvalues. You should be able to guess what they are. For example, the first one is going to be equal to 2. The second one is going to be 3. I recommend listing them in the same exact order you did here, but keep in mind we have this additional lonely little 0 eigenvector of 0 at the end, so we're going to have 3 independent eigenvectors that we need to find here. So the first eigenvector is going to be 1, 0, and minus 1. The second eigenvector for 3 is going to be equal to 1, 1, and 1. And the third eigenvector is going to be equal to 1, minus 2, and 1. Right? Keep in mind, these are symmetric matrices, so you should be able to find exactly n of them for each of these matrices. Now, these are not unit vectors, so for example, we need to divide this one by the square root of 2, we need to divide this one by the square root of 3, and we need to divide this one by the square root of 6 in order for them to be unit vectors, but those are going to help us build our matrix U. Once we have that, then we can find our singular values. For example, singular value 1 is going to be the square root of the first eigenvalue of 2, and the second singular value is going to be the square root of the second eigenvalue, which is going to be equal to 3. So that gives us our matrix U, V, and these are going to help us build our matrix D. So let's look at our eigenvalue decomposition. Our singular value decomposition. So we have 1, 1, 0, 1, minus 1, 1 is going to be equal to, so the first matrix is going to be this nasty one, so the over root 2, over root 3, over root 6 matrix. So that's going to be equal to 1 over the square root of 2, 0, negative 1 over the square root of 2 for our first column. Then we have 1 over the square root of 3, 1 over the square root of 3, and 1 over the square root of 3 for our second column. And then 1 over the square root of 6 minus 2 over the square root of 6, and 1 over the square root of 6 for our third column. And you should be able to check that the determinant of this matrix U is equal to positive 1. That means the determinant of our V matrix must also be equal to 1 as well. And then we have our D matrix. This is going to be the same size as our original, so a 3 by 2. So we're going to have the square root of 2 and the square root of 3. Make sure they are in the correct positions. And then we're going to have our lonely 2 by 2 matrix here, 1, 0, 0, 1, and then we take the transpose of it. Yes, I know it's the same exact thing, but keep in mind you have to check before you do anything that the determinant of that is equal to 1, and they do match. Therefore, once they do match, and those are indeed unit vectors, that means this is the singular value decomposition of that particular matrix A. Now, a couple other things that are very important to keep in mind in terms of definitions. The first is going to be what is called the condition number. So the condition number for any matrix A is actually equal to the ratio of the maximum singular value and the minimum singular value. So if we look at this previous example, that's going to just be the square root of 3 divided by the square root of 2, which is approximately 1.22. You should be able to see that from this definition, one property that is satisfied for the condition number is that the condition number for square matrices, or actually any matrix, is always greater than or equal to 1. And that's for any matrix A. Right. Now, in terms of the interpretation of the condition number, generally speaking, if the larger the condition number, the more ill-conditioned the matrix is. Usually means when you put this into a computer and, for example, do inverses and calculations, it's probably going to give you a lot of potential errors. So you definitely need to be careful if your condition number is too large, because you might have a lot of truncation error, round-off error, and all those things. So big condition number, a lot of potential error, but that's more of a numerical analysis discussion. So I'll just leave this definition here, and we'll discuss it later when it's more appropriate. Now, another thing that singular values actually have in terms of applications is actually connected to the norms of matrices. Up to this point, we've actually only discussed the norms of vectors. For example, if I have 3 minus 2 and I ask you to find the norm of this vector, you're probably going to say that this is just going to be equal to this 3 squared plus minus 2 squared, which is just going to be the square root of 9 plus 4, which is actually going to be equal to the square root of 13. Now, what I actually would invite you to do is find the singular value decomposition of this vector, right? Because it's just a matrix, so it has a singular value decomposition. But in particular, find the singular value of this matrix. You should be able to say that there's only going to be one singular value because it's a 2 by 1, and the minimum of 2 and 1 is 1. And in particular, the singular value is equal to the square root of 13. And one should be able to prove, from that example at least, some sketch of a proof, that the norm of a vector is actually going to be equal to the singular value of that matrix. So this actually leads us to potentially define the norm of any matrix. So let's define the first norm. So let's assume A is an m by n matrix. Then what we call the L2 norm of A is given by the norm of A subscript 2 is equal to the maximum singular value. So for example, if we go back to that other example that we had, for example, 1, 1, 0, 1, minus 1, 1, and I ask you, what is the L2 norm of this? You should say that that's going to be equal to the square root of 3. Right? Now, is this the only definition of a norm that one could take? And of course the answer is no. And in a more advanced discussion of linear algebra, one would at least, explore the different norms and the pros and cons, or the equality or equivalency of all of them. So I'll actually introduce another norm that is actually quite intuitive. Again, let's assume that A is an m by n matrix. Then what we call the Frobenius norm. So the Frobenius norm of A is given by, and this actually looks a lot like the definition of the norm for a vector. And this is going to be the norm sub A subscript F, and this is going to be equal to the sum, or the square root of the double sum of A, J, K, the quantity squared. Right? So for example, if we take the Frobenius norm of 1, 1, 0, 1, negative 1, 1, that's just going to be equal to the square root of 1 squared plus 1 squared plus 0 squared plus 1 squared plus 1 squared plus 1 squared, which is just going to be equal to the square root of 1 plus 1 plus 1 plus 1, which is going to be the square root of 5. Now, what does this have to do with singular values? Well, one should be able to prove, at least in theorem form, that this is actually equal to the sum of the square of the singular values. Right? And for our example, that's just going to be equal to the square root of the square root of 3 squared plus the square root of 2 squared, which is of course the square root of 3 plus 2, which is the square root of 5, which is indeed the same exact thing. But those of course do not produce the same exact norm, and hence they have different names. Now, is there any relationship to these norms? The answer is yes, and I'll leave this theorem for you. But for all matrices, A, which are m by n matrices, the L2 norm of a matrix is actually always less than or equal to the Frobenius norm. For this, we clearly see that that is the case, but it actually is true for all matrices. So if you prefer smaller numbers, the L2 norm is probably for you, and the Frobenius norm, of course, would be larger. So if you like larger numbers, then that would be your preference. But these are not the only two norms in existence. There are infinitely many others, but those are the only two that I want to introduce today. So those are some of the basics associated to singular values, singular value decompositions, how to find them, and a couple little applications and sub-definitions associated to the condition number and different types of norms that you could definitely explore on your own, or when we return to them later on in linear algebra discussions. So until then, I hope you enjoyed this video. Take care.